Okay, so in this one video, we're going to be doing some example problems for wave speed. Remember that the speed of a wave, or the velocity, is frequency times wavelength. If we look at the units, velocity would end up being in meters per second. Frequency would be measured in hertz, which is the same thing as 1/seconds. A hertz is a cycle per second, so a cycle doesn't really have like a unit. So we just put 1/seconds. Sometimes you'll see it written as this, which from math class, if it's to the -1, just means it's on the bottom. And lastly, our lambda is going to be in meters. Now, could lambda be in something else, centimeters? Yeah, sure. And if that is the case, just leave it. That's perfectly fine. Also, our velocity could also be equal to lambda over the period. If we remember, the period is a time measurement, so it'd be measured in seconds, or some time frame, a day, a second, millisecond, something like that. And so this has a unit of seconds, and it's just a time, so it's how long it takes for one cycle. I also wrote down that frequency is equal to 1 over the period, so therefore the period is equal to 1 over the frequency. So keep this in mind when we are doing these example problems. All right. So I attached in a file the problems, okay? And they come from the book in class, not the online book. So I'm going to put down like given and find, but you could actually read the question yourself. All right, I'll read it out loud first. Number 1, example 1. It says a piano emits frequencies at a range from a low about 28 hertz to a high of about 4,200 hertz. It says find the range of wavelengths in air attained by this instrument when the speed of sound in this air is 340 meters per second. I want to keep putting the vector over v. If you did that, I wouldn't think anything of it. So here's our first frequency, here's our second frequency, and basically all we want to know is the wavelengths, okay, produced by those two. So this is the speed of sound that they picked. Speed of sound, which we'll get to, actually fluctuates depending on the temperature of the air. So the higher the air, the hotter the air, the faster it moves. The colder the air, the more dense it is, the slower. All right. So first off, we have V equals F lambda, and so therefore lambda equals V over F. So we're going to, for the first one, we'll put in lambda equals 340 divided by 28. Nice thing is I have the answers here in front of me. And so we get 12. Sometimes I don't trust the book. I'd rather do it myself. So 340 divided by 28, yep, 12. We'll go with two significant figures too, because we'll say the first one's 2 and the second one's 2. You know that 0, I have issues with books, they never label the zeros, but it doesn't matter. 28 hertz, two significant figures. In our second one here, we're doing 4,200, so lambda is equal to 340 divided by 4,200 hertz. That's pretty messy. 4,200 hertz, and we get 0.0081 meters. Okay. So basically, we're leaving this the same for each one, and the higher the frequency, the lower the wavelength. The lower the frequency, the higher the wavelength. So our range would be from this to this. All right, number 2. It says The speed of an electromagnetic wave, so an example of electromagnetic wave would be light or a radio wave, stuff like that. In empty space is 3.00 times 10 to the 8th meters per second. I think that's like 7.2 or 7.3 times around the Earth in 1 second. That's how fast electromagnetic waves travel. It says calculate the wavelength of the electromagnetic waves emitted at the following frequencies. So it gives us a frequency. I'm only going to do one. Visible light. Visible light has 6.0 times 10 to the 8th megahertz. Now mega means times 10 to the 6th. Okay. So this would actually be 6.0 times 10 to the 14th hertz. And we're finding the wavelength. So V equals F lambda. Lambda equals V over F one more time. 3 times 10 to the 8th meters per second divided by 6.0. Do it with the calculator. Oh, I skipped the 3.0. So 3 to the 8th divided by 6 to the 14th. This calculator does not work. And we get 5.0, two significant figures, times 10 to the negative 7th meters. Now, one of the big mistakes, I think it's pretty obvious what would be in this one, is that people wouldn't convert from megahertz to hertz. All right? Next. Red light. It says number 3, it says red light is emitted from a helium neon laser with a wavelength of this. And then tells you how fast it travels. It says find the frequency. So for example 3, I'm not going to work through that, but example 3, we are given a velocity and we are given a wavelength, and we're trying to find the frequency. Be careful with the nano, it's at times 10 to the negative 9. All right, and number 4. A tuning fork produces a sound, frequency 256 hertz. So the frequency, 256 hertz. And the wavelength in air, 1.35 meters. And it simply wants to know the velocity. So, velocity equals frequency times wavelength. Frequencies, 256 hertz. The wavelength is 1.35 meters. And our velocity would be 346 meters per second. Okay? So, if you recall in the other problem, it said that we're going to use 340 for the speed of sound in air. Okay? In this one, it comes out to 346. So the one thing we know is that the air must be a little bit warmer in this problem. And so this leads to another aspect of sound, which we haven't really got to yet, but I'll mention it now. There's a second part. So this is A. In B, it says, okay, how about if the sound traveled at 1,500 meters per second? That's like 4 to 5 times greater. Okay, it says what would the wavelength of the wave produced by this tuning fork in water? So here's the thing. If you ever want to see if a train's coming, you should look. 1. 2, you can put your ear down to the steel and listen, and the sound will get there faster through the steel than it will through the air. Same thing with water. Sound travels faster in water than it does in air. So if we look at density, cold air is more dense than warm air. But sound travels slower when the temperature goes down. Now, water and steel or metal are obviously more dense than air. But the same thing doesn't happen, okay? It doesn't slow down because it's more dense. It actually speeds up because the molecules are closer together, okay? It's able to transfer the sound wave better. So I always make this statement, if we're talking about the same substance, water, and then cooler water, okay, it travels slower. But if we're talking about two different substances, the more dense one travels faster. Sound travels faster. All right, and so anyway, the last thing they want us to do here is what would be the wavelength produced by this. So I'm gonna kind of shortcut this, V over the frequency, okay? And so I have my velocity, I have my hertz, 256. For some reason today, I am missing numbers. And we're looking for the wavelength. Looking for the wavelength. 5.86 meters. 5.86 meters. I tell you, they mess around with these significant figures in the book, but if you have it written down as just 5.9 meters, that'd be perfect. So you notice here, we have faster velocity, same frequency, has to be a bigger wavelength. Right? Now the one thing in this that we did not go over is the period. So why don't we take a look at one of these and we'll figure out what the period is. Okay? So frequency is so we don't really need the speed to figure out the period. You recall that velocity is equal to the wavelength divided by the period. We don't need that, okay? As long as we know what the frequency is, we could just figure it out that way, okay? And then maybe we'd have to take that and then plug it in here or whatever to find our velocity, okay? But anyway, the period is equal to 1 over the frequency. And so the nice thing is on the calculator, all you have to do is type in 256, and it's an inverse, it's a flip. So there's an x to the -1 button. It's normally over here above 7. It has the EE above it, which I use all the time, and it flips it for us, and we get 0.0039, and it'd be seconds. If we take a look at the units, right here, we would have 1 over hertz. And if you recall, hertz is 1 over seconds. So, does the flip, right? When you divide, you multiply by the, I forget, what's it called? By the reciprocal? Anyway, it leaves us with S, seconds. Yeah, it's reciprocal. Reciprocal. Tell me I'm wrong. Okay. So they're just some real short, simple wave speed problems. Okay, we don't want to get anything too difficult here. When we get the sound, we'll have a correction for the speed of sound in different air temperatures.